Hello, everybody. Right, okay, this is probably not going to be my best ever video because, yeah, making it under a bit of time pressure because I know you want it and I don't have all that much time in my life at the moment. So this is not sort of strictly part of the Learn Some Python with Jordan and Jackie series because this one is specific to the 2023-24 iteration of product engineering, and it is the first of two videos that I'm going to make about, well, in order to give you some guidance and help with the programming side of your group project. As you can tell, I'm doing it in English because I would never be able to do this in Dutch. Okay, so part one is going to talk about the algorithms, the logic of your robot, of, yeah, of what you need to do. And then I will make another one that'll instead focus on sort of some of the Python structures that you could use to achieve that. Okay, let's see. Right, I am going to talk only about the easy and medium versions today. Basically, if you think you're up to doing the hard, then you're going to need to work that out for yourselves. Remember that with the medium version, if you do it all right, correctly, well, you can get 9 out of the available 10 points. So that's a very good grade. I think that would be what most groups in the class should aim for. And yeah, if you want to do something more advanced than that, then you need to be happy, willing, able to go the extra mile. Okay, so we'll start with the easy. So just to remind you, what the easy needs to do is your robot needs to start over here. There'll be some sort of a wall on the edge of the arena, which is going to be roughly 1 square meter. And when you you switch it on, you put it down, and then it needs to have a button of some sort. I suggest you use the touch sensor from the connected interaction kit. When you press that, it needs to drive as straight as possible, drawing on the paper, and then it needs to stop just before the wall. I'm not too fussy about the distance, close but without hitting it. So then it needs to stop there, at which point you will pick it up and place it like over here, and then press the button again, and then it should drive straight again, stop when it sees the wall, then you pick it up, put it there, press the button again, boom. If you wish to also include the pen movement mechanism, then while it's doing each of these lines, the pen should sort of be moving side to side so that it draws a vaguely sinusoidal oscillating line as it goes. Okay, so that's what we're trying to do. Now let's have a look at the algorithms that might achieve this. All right, so I'm not sure to what extent you're familiar with both of these concepts, finite state machines and flowcharts. So flowcharts, I imagine you've seen before. Also in the workshop manuals for week 6, 7, 8, when you cover programming type things, I include flowcharts for most of the programs that you're making. So just briefly, a flowchart kind of tells you the flow of an algorithm or a program. Starts at the top, does this thing, then does this thing, potentially goes back. Try to be as consistent as possible with the fact that these sort of oval ones are the beginning and end of programs or parts of programs. These parallelogram ones are generally either output to a device or input from a device. The diamonds are checking something, a conditional, an if statement, a question, and then the square, well, the rectangular boxes are just kind of doing some kind of processing. Now, a finite state machine is a different thing, very useful tool for conceptualizing algorithms and, in fact, for structuring programs. And in part 2, I'll show you how to make a very simple implementation of a finite state machine in Python. So, if you've never heard of one, give it a quick Google, look on Wikipedia, ask ChatGPT, whatever, just, look it up, just find out the basics. So the basic idea is that a finite state machine represents the behavior of a thing, often a program, in a finite number of states, so a countable number. And basically, in the context of something like this robot, it allows you to have completely different behavior under different conditions. And then So the two things that make up a finite state machine conceptually are the collection of states. So I'll talk about this more in a sec, but here we have the wait state and the clean state. And then the arrows represent the transitions between states, and the writing next to those arrows represents sort of the conditions under which those transitions happen. So this is a super simple one, about as simple as you could get. And yeah, it's basically just a good way of allowing different things to happen under different conditions. So for the easy version of the robot, we only need two states. We need the wait state, which is how it starts, you know, when it's just sitting over here waiting for us to press the button. And we have the clean state, which in this case is what I'm calling the drive straight, optionally wiggle the pen around, you know, pretend to clean the surface. So we have these two different states, and there are transitions possible both ways. So when you're in the wait state, the thing that moves you to the clean state is the button. I've said pressed/released because it's up to you whether you want to trigger when the button goes from low to high, i.e. when your finger touches the button, or probably a better idea for, well, a better idea because it'll lead to your robot being more likely to go straight away, is if you instead trigger when you press and then release the button. So detecting when your finger is removed from the button, and at that point changing to the clean state. And the advantage of that, doing it that way, is that then your finger is out of the way before your robot starts moving. We'll talk about how you do that later. Okay, so pressing the button takes you from the wait state to the clean state, and then the thing that takes you back to the wait state is basically the time of flight proximity sensor. If it sees something close enough, i.e. sees the wall close to the robot, then you go back to that state. Now, in your code, as we'll see in part 2, you basically use if statements, well, in the easiest possible way, which is what we're going to do. You use if statements to sort of do the code associated with these two different states, depending on which state we're in. Here I just show the algorithm. So in the wait state, basically, when we first enter the wait state, which will be when we've turned the robot on or when we've come back into it from the clean state, we need to stop the drive motors, stop the servo motor. Then we just need to see whether the button is triggered, depending on how you want to detect it being triggered. That's up to you, but we're just saying, you know, has the user activated me? If not, then we just loop back and we keep checking the button, and we just keep doing that. And then eventually when the button is triggered, we go onwards and we switch to the clean state. So over here, we enter the clean state. Then we want to calculate the necessary powers for the motors, calculate the necessary position for the servo. Then we update the motors and the servos with those values. Then we check our proximity sensor and we say, do we see something within the threshold distance? If we do not, then we go back here, we calculate the motors again, calculate the servo again, send those values to the motors and servos again, check the proximity again. And we keep doing that until eventually we do something, see something close enough, and at that point we go back to the wait state. Yeah, so these sort of outline in a slightly abstracted way the algorithms associated with each of these two states, and then this is sort of the overall thing, the overall logic of the behavior. Okay, so that's the easy. Now let's have a look at the medium. So just to remind you, it's a kind of similar thing, except now the turning has to be automatic. So our robot starts here. Again, it waits for us to press the button to tell it to start. Sorry, just drinking some water. When we do, it needs to drive as straight as possible. It must then detect the wall from a slightly further distance to give itself space to do the turn. And at that point, it needs to turn 180 degrees to the right. Notice that the ideal distance between the two straights, dr, is the diameter of the robot. And what that means is that you can do this turn by just stopping one of the wheels and driving the other wheel, because if you stop the wheel on this side, then the robot will do a turn sort of centered on that wheel, the pen's in the middle, and so that means we'll go from the robot being like there to the robot being there. Yeah, so I intentionally made that the distance I'm asking for because it makes it a bit easier. Right. So we drive straight, we see the wall. When we do, we trigger the turn. We turn hopefully exactly 180 degrees. Then we drive straight again. When we see the wall, we're going to turn, but note that this time we need to turn to the left instead of to the right. So we do that. Then we go straight, see the wall, turn to the right again, straight, and the fourth time we see the wall, we don't turn, we stop. And ideally, I can't remember if I said this is a requirement or not, but we should then go back to the wait state so that we could start that whole process again. And once again, optionally wiggling your pen around to make a roughly sinusoidal path along here, which we would want to do during the turn as well, though of course it'll look a bit less sinusoidal during the turn because we're curving as we draw. Okay, so how do we do that? Now, don't be alarmed. The first finite state machine I'm going to show you looks like a mess. There we go. Okay, so this is what we would need to do if we wanted to describe the necessary algorithm with a pure finite state machine. Doing it this way, compared to the way I'll show you afterwards, is conceptually just a little bit easier, but it's a lot less elegant. It's very inelegant, in fact, because with all of these states, so essentially what we have here is a state for each of these turns and straights. So the first straight, the first turn, the second straight, the second turn, the third straight, the third turn, and the fourth straight. So conceptually a little bit easier, but inelegant, and you're going to have to repeat a bunch of code inside all of these states, because the first straight is basically the same as the second straight, but in order to keep track, this is all about the fact that we have to sort of keep track of how many straights we've done and eventually stop, and also the fact that we're turning right and then left and then right again. So, not the end of the world having to repeat that code. You can copy paste and make the necessary tweaks. So you might choose to do it this way because it is conceptually a little bit easier. It's not how I would do it, and yeah, we'll come to that in a second. Anyway, so in this case, we start in the wait state. When we press the start button, we move to the first straight state. We stay there until we see something within the proximity threshold. Then we go to the first turn state, in which case we turn right. Once we have turned 180 degrees, we move to the second straight state. Then when we see the wall again, we move to the second turn state where we're turning left. When we've turned 180 degrees, we go on to the third straight. Then when we see the wall, we go to the third turn, which is right again. Then when we turned 180, we go to the fourth straight. And finally, when we see the wall, that time we go back to the wait state. Blah, what a mess. Anyway, if we're going to do it this way, let's have a look at what the flowcharts for the individual states would need to look like. Okay, so the wait state is basically the same as it was for the easy. We enter the wait state, we stop everything, we keep checking the button, and eventually when the button is triggered, we go to, in this case, the first straight state. Now, notice that I'm not showing the flowcharts for all of the straights and all of the turns because they're very, very similar to each other, and I didn't have time / space on the slide. Okay, so in the first straight state, this is very similar to how it was in the easy. We start, we calculate the motor powers, we calculate the servo position, we update the motors and servo with those. Then we check whether we see something within the required distance. If we don't, we go back, we recalculate, boom, 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 we check again, boom, 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 we check again. And eventually when we do see something, we switch to the first turn state. So here we come. Now for this, what we need to do is calculate the servo position because we need to keep oscillating that pen while we're turning. Then what we need to do is, and there's some small differences in how you could do this, but basically we need to stop the right motor and drive the left motor so that we turn to the right. We also need to update the servo with this value from here. And then one way or another, we need to figure out, have we turned through 180 degrees yet? If we've not, we go back, we calculate the servo position again, we continue to keep the right motor stopped and the left motor driving, we update the servo with the new angle that we've calculated, we check again, we keep doing that for as long as we need to, and eventually when we have turned 180 degrees, we come out here and we switch to the second straight state. So then you're going to need to duplicate these with very slight modification. So for the second straight state, it's basically identical to the first one, except that we transition to the second turn state afterwards. And the same for the third straight state, where we also just transition to the third turn state. And then with the fourth straight state, it would also be the same as this, but we would transition to the wait state. So essentially just bloom, 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 back to the beginning. Those are the scientific noises for those things. Right, and then in terms of the turn states, they would also be very similar, except that the first and third turn state are identical to this one aside from where they go next. But the second one, you would just flip this around here so that you're stopping the left motor, driving the right motor so that you turn to the left instead. Okay, so that is the sort of the brute force approach. Now let's look at a slightly more elegant, well, no, I would say a significantly more elegant, slightly more complicated version that uses what's often called an extended finite state machine. So conceptually, the difference with the extended finite state machine is simply the fact that if you want to, you are allowed to give the states memory. You're allowed, they are able to potentially remember information from things that have happened in previous states. So the key thing that we need in this case is the ability to remember how many turns we have done on this pass through, on this cleaning iteration, you know. Yeah, so for each time we are put in the left and we start, we need to, so at the beginning we've not turned at all, then we've turned once, then we've turned twice, then we've turned 3 times. We just need to be able to remember that. Now, in practice, the way you'll probably do that, the easiest way to do that, and the way I will suggest that you do it, is just with a global variable in your program that all of the states can look at. There are other fancier ways you could do it with, yeah, there are fancier ways you could do it, but we won't worry about that. So by extending our finite state machine with the ability to count how many times we've turned, this whole thing simplifies down to just 3 states, because now we just need a wait state, a drive straight state, and a turn state, where these all do slightly different things depending on how many times we have turned. So we start in the wait state. When the start button is pressed, we go to the straight state. I know I called it the clean state in the easy, but that's because, well, yeah, but the reason I changed to straight is because we're cleaning during the straight and during the turn this time. Anyway, so we transition to the straight state, and the state knows how many times we have turned, and at the moment, that number is 0. So we drive straight. When we eventually see the wall close enough, then where we go depends on our turn counter. So if our counter is less than 3 and we have seen the wall, then we follow this branch, right? See, proximity is less than threshold and hash is less than 3. When it eventually hits 3 and proximity is less than threshold, we'll go somewhere else. So first time around, we hash is 0, so we go there. Now we enter the turn state, and we'll see in the flowchart in a second how we do this, but we turn either left or right, depending on the number of turns that we've done. Then we increase our turn counter by 1. The only way out of this state is when we've turned 180 degrees, one way or the other, so then we go back to the straight state. Cool, then we drive straight. We see the wall, we go back to there. We turn, we go back to there. We see the wall, we go back to there, we turn back to there. Now that was the 3rd time we turned, and so at this point, when we again reach the wall, hash is equal to 3, and so we take this branch out back to the wait state. Okay, let's have a little look at how those look as flowcharts. So the wait state is identical, except that now whenever we're in the wait state, we need to set our turn counter equal to 0. Because, yeah, whenever we're in the wait state, that's sort of starting the sequence of 4 straights and 3 turns. And then, as before, we stop the motors, we keep checking the button until eventually the button is triggered, and then we switch to the straight state. Boom. So here, this is very similar to the previous versions of the go straight. Calculate the motor powers, calculate the servo position, update both of them, check for the proximity threshold. If we're not there yet, we do that again, do that again, do that again. Eventually, we see the wall. Now, here's where the slight difference comes in. We come to another check, and at this point, we say, is our turn counter less than 3? If it is, we go to the turn state, boom, over here. Okay, now this one also needs to change a little bit because now we need to turn right and then left and then right again. So the best way to do this is to look at hash, how many times have we previously turned. So at the moment we're coming into our first turn, so this is 0. 0 is even. And therefore we take this branch, we stop the right motor, we drive the left motor, therefore we turn right. Then we calculate the servo position, we update the servo, we check whether we have yet turned 180 degrees. If not, we go back to here. The left and right motors are still just doing what we last told them to do. We calculate the new servo position, we update the servo, we check if we've turned 180, maybe not, do again, until eventually we have turned 180. At which point, we increase our turn counter by 1, because we've now completed 1 turn, whoops. And then we go back to the straight state. And we do the whole thing again, and then we do this whole thing again, but now hash is equal to 1. So it is not even, which means we go here, we stop the left motor, we drive the right motor, so we turn left, and we go through again, then we go back to here. And then eventually, once we have turned 3 times, we go back to the straight state, boop, 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 boop. We get down to here, and now our turn counter hash is no longer less than 3. Now it's equal to 3, and so we take this branch and we go back to the wait state. Okay, so that is that's the algorithm level of what you need to do. Now, the last thing I'm going to include in this video is some similarly sort of abstract high-level tips for how to achieve some of the specific things described in the boxes of these flowcharts. Okay, let's start with the fairly straightforward ones. So, checking whether your button has been triggered, however you want to do that. In Workshop 6, Sensors, we are going to do a basic version of this, and I'm also going to, in the workshop manual, give some guidance for how you would make the code a little bit more complicated in order to specifically detect rising edges or falling edges in the button signal. So what does that mean? How do I make this? Can I make this a pen? Yes. Okay, so a button gives a digital signal. So that means it is either low or high or low or high. So yes, you can in your code, you can just say, is the value low? Is the value high? You can totally do that. But often what you actually want to do is go, has it just changed from low to high, which would be a rising edge from low to high, or has it just changed from high to low, which we call a falling edge. Yeah, so that's not particularly hard to do. And Workshop Manual 6 will give you some advice on how to do that. Okay, for the proximity is less than threshold. So again, in Workshop 6, we are going to see how to read from the proximity sensor. Any of you who did digital interfaces last year would probably have done that already. It's quite easy. And then comparing that range value to a threshold is also very easy. It's just an if statement with a comparison. So in Workshop 6, we'll read from the sensor. We won't specifically compare it to a threshold, but yeah, that extra step is not very hard. And then the sort of updating, sending new values to the motors and to the servo. So that we're going to do in Workshop 7. So one of the tasks will be interfacing with a servo, just sending angles to it, show you how to do that. Another of the tasks will be interfacing with the motor driver board that you got in your robot parts kit. To just, send speed and direction commands to the motors. Now note that, so in fact, all three of the programming workshops have the option, which I think most of you would not have time to do within the workshop, but you could certainly do afterwards in your self-study time. You have the option to take the functionality that we develop over the course of the workshop and encapsulate it in a class. What is a class, you might ask? Well, that is addressed a little bit in the workshop manuals and also in one of the videos from my video series that I've been making with Jackie Bourgeois, who anyone who did digital interfaces will know him from that. He's the Frenchman who teaches that course. So over the past few, couple of months, Jackie and I have been making a series of videos called Learn Some Python with Jordan and Jackie. Just today, I have uploaded the videos that we've got so far to YouTube, and I'm going to be linking those in Brightspace. And so by the Monday of week 6, you'll have access to those videos. As you will see, quite a lot of those videos cover small specific topics like how to use if statements, for example. I also have a longer one on what classes and objects and object-oriented programming is all about. And there's also one that I think you'll find quite helpful on how to sort of effectively use ChatGPT to help you program while not stopping you from learning. Anyway, yeah. So our video series, I think, will be helpful for some of the details of how you do all sorts of these things. And these things are all to varying degrees addressed in the upcoming workshops. Okay, then these things are maybe, I suppose the slightly harder ones. Okay, so the workshop's going to show you how you send an angle of your choosing to the servo, but how should we calculate what that position should be? Well, if we want our pen to draw a roughly sinusoidal wave, then it depends a little bit on how you design the mechanical mechanism. But basically, you're going to need your servo angle to change over time with some sort of a periodic function, and quite possibly a sinusoidal periodic function like a cos 2 pi ft. Might well be the sort of thing you want to do. So whatever function you use, notice that time is going to need to be in that, right? Because that's how you're going to get the servo to go from left to right at a sort of consistent pace. So you're going to need to use a module in CircuitPython that we're going to use in, I think, all of the workshops. The time module, one of its functions is monotonic. It's explained in workshop 6 and 7 to varying degrees. But basically, it gets you the time from a clock on the processor that just always counts up while the process is running. So you're going to use that in one way or another to get your t. Then you just have to code up a function like this one. If you want to use sine or cos, that comes from the math module. So you can use math.cos to get this. And then you just multiply it by some sort of amplitude, and in the brackets put 2 pi because these cosines use radians. So 2 pi times the frequency at which you want it to wiggle back and forth times the time. So that can be done in just one line of code. It's not particularly hard. Okay, now there's this, what I just calculate the motor powers. Easy, right? Okay, so in order for our robot to drive straight, we need our motors to turn at the same speed, right? Because it's differential drive. Like Ernest told you in the kinematics week, if we want to drive a curve, then we need our inside wheel and outside wheel to drive at different speeds. And therefore, if we want to drive straight, then we need our left and right wheels to drive at the same speeds. Now, workshop 6, 7, and 8 sort of build up towards, in workshop 8, showing you how to do closed loop control, where you use a sensor signal to modify the input to your actuator based on what you want the actuator to be doing. In workshop 8, we're going to look at how to do PID. So we'll cover this in class, but Google it if you want to know ahead of time. We're going to do PID, closed loop control of the speed of a motor. using a signal from the rotary encoder, which is one of the little, the component that you've got, the little circuit board that you've got two of in your bag of robot bits, which works with those little black wheels with the slots on, to measure how fast the motors are turning. Using the encoder to measure the speed we're going to do in workshop 6. But both of these workshops are going to encourage but not require that you take the code and encapsulate it in a class, which would make it a little bit easier to integrate it into your overall robot code, but that's not essential. Yeah, so we're going to, I mean, we think this is an important concept for you to learn. It also includes some very handy electronics and some handy coding tricks and stuff like that. However, I have to admit, so just over this week, I've finally done the coursework myself, and my robot is working reasonably well. I only had about, I don't know, 8 hours to spend on it in total. So I think I might hope that some of you do a bit better because you have a bit more time and effort to put into it. But I have at least confirmed that it works well enough that I know it's possible. But I have to admit that doing PID speed control of the motors doesn't work all that well. And really the reason is because the hardware we've got is cheap. Specifically, the motors are quite cheap. They're a little bit sort of variable. And a key issue is that the encoder disk rotates at the same speed as the wheel, because they're just on opposite ends of the same drive shaft, which means we don't get all that many encoder counts per revolution. Whereas if you were to buy a more expensive motor with an encoder, then basically the encoder would be on the motor shaft before the gearbox that slows it down and increases the torque. And therefore the encoder would spin much faster. You'd get way more counts from it, way more information, and you would be able to much better control the motor. Anyway, I did some tinkering and I got it working reasonably well, so that my motors go at quite similar speeds. Don't overly stress about it. I am aware that the hardware is cheap and that it is difficult to make the robot go perfectly straight. So I'm not going to be like, I'm going to tell the coaches not to be super strict about straightness. But nonetheless, we encourage you to try and do it this way and get it going as straight as possible. To some extent, the grading will sort of be relative, right? So if everybody's robots are going a lot straighter than yours, then you probably won't score as many marks as they do. But it is important for you to know that if this whole PID control thing is really stressing you out and it's not going so well, it is also possible to just go with open loop control, which essentially means you just drive the motors at some fixed power. You might want that power to be slightly different for your left and right motors because the motors, being cheap, are not identical to each other. Some are a little bit faster than others. But yeah, so I wouldn't encourage this, but if necessary, then instead of calculating motor powers, you can just say motor left gets 0.45, motor right gets 0.49, and you can find those numbers just by tweaking and see what leads to your robot going relatively straight. So that is an option. I don't particularly mind if you do that. I mean, I definitely want you to do the PID control in the workshop as the workshop task so that you understand that. But yeah, keep in mind that there is a simpler option than this, which might work less well. One of the key issues with this is that it's going to be much more sensitive to, for example, as your batteries start discharging and things slow down, there will be no compensation for that. But yeah, so that's the basic. So basically, the ideal way where we do proper speed control of the motors, that's going to be covered in workshops 6, 7, and 8 altogether. But if necessary, you can just tune the powers to the two motors and do it without the sensory feedback. And then finally, this question of have we turned 180 degrees? Essentially, there are two fundamental ways that this can be done. Option 1 is based on time. So you could use time monotonic, which we will use in all sorts of other contexts. in order to keep track of the time that you've been turning, you can then sort of experimentally determine how long it takes for your robot to do 180 degrees. That might work better if you're controlling the speed of the driving wheel, but you could probably get something relatively close to 180-degree turn with just a fixed power input to the one wheel and timing. But if you went that route, then you would really be very susceptible to changes in your battery charge, because as the batteries go flatter, the motor goes slower, and suddenly you're only turning 120 degrees because you're not compensating for that. And then the other option is to use the information from the encoders in a different way to how we would use for speed control. You can, there are 20 slots in the disk, so for every rotation of the wheel, you get 20 encoder counts. You can use basic maths to work out how many times you need the left wheel to turn. It might be like 1.7 rotations or whatever is what you need to get 180 degrees of turn. And you can do that by looking at the diameter of your robot and work out the circumference of half of the circle, and then look at the circumference of your wheel and so on. So your second option, which is how I did it when I did the coursework myself this week, and I think it is probably the better way to do it, is to work out how many encoder counts corresponds to 180 degrees of turning, and basically drive that wheel, stop the other wheel until that many counts have been received. That might require you to use the encoders in a slightly different way to what we're going to cover in the workshop, but I suppose if anything, it's in a simpler way. So I think you can figure it out. Yeah, and I would say that is a better option, because that way, if your batteries are a bit flatter and therefore your motors are turning slower, that's fine, because you will still drive for a fixed number of rotations rather than a fixed amount of time. Okay, right. Wow, that was, as always, a bit longer than I was planning. I hope when I ultimately give this to you, you find it to be helpful. And later today or tomorrow, I will record part 2, where I will focus instead a little bit on how to build like the finite state machine in Python and structure your code overall. Okay, that's it for now. See you next time. Bye.